Good afternoon, good morning, or good night, everybody. So today we have the pleasure to have here Dr. Antun Domic. Now I give the floor to Rafael Brum, the session chair of today, to do the presentation of Antun. And Antun, thank you very much for accepting our invitation.
Thank you, Ricardo. Before we start, I'd like to thank you all for the audience. We have people from the US, from Chile, Canada, and literally everywhere in South America watching us right now. And this event became much bigger than we ever imagined. So thank you once again. So today we have Professor Antun Domic, who is a lecturer in the Department of Electrical Engineering at Stanford University in Palo Alto, California, and also an advisor to several technology startups. Antun has a long and successful career, and after his PhD, he taught mathematics at the Universidad Técnica do Estado and Universidad de Chile in Santiago, Chile. He was R&D vice president at Cadence Design Systems, responsible for place and route tools. He was general manager of the design group in charge of logic synthesis, timing, physical design, and analog simulation tools of Synopsys. He was also the CTO of the company till his departure in 2019 when he became a lecturer at Stanford. He's a IEEE Life Fellow and was recipient of the 2019 IEEE Robert Noyce Medal. So, Professor Antun, it's really an honor. Thank you for being virtually here with us, and the floor is yours.
Okay. Thank you very much, Rafael, for your kind words. So, how do we get the presentation on now? Oops.
Sorry.
What do I?
I'm giving to you the.
Okay.
Sorry. I have to switch to your slides now.
Okay, that's very good. So thank you, Ricardo, and very pleased to be here. Thank you for inviting me. So this is a presentation on a very old topic. So let me tell you a little bit of what's the story of this. A few years ago, 3 years ago actually, Stanford reestablished a class in EDA. They hadn't had one in a long time. And Raul Camposano, myself, and Patrick Grunenwald did this quarterly class. We have done it 3 years now. And one of the topics that we selected was timing models, of course, for cells and some delay estimates. And that's how we went into Elmore delay, because it was the simplest. And second, it is still widely used in tools today. So when I began to look at the literature, of course, you go back to the famous paper of Rubinstein, Penfield, and Mark Horowitz. That paper is, I think, 1983, so it's even before some of you were born. And the formulation and everything is correct, by the way. But the part that I was not totally happy in teaching it is that if you want to do the full deduction, results of network theory get called. And I said, well, if this is the case of a tree, can we do it more directly? So I'll talk about that part, and I'll nose dive into it because we don't have much time. If any of you is interested in some introductory material like the different timing models that are used for cells today and other pieces, I would be very happy to send you the slides. Send me an email to domic@stanford.edu, and I'll send you the more complete set. So let's go pretty directly into a tree, and let's look at what's the problem that we're trying to solve. What you see here in this light circle would be the reduction of a gate, let's say an inverter, into a voltage source and a resistance capacitance pair. They are R1 and C1. This is fixed. And this is the part that I'm skipping. How do you get to here? And from here on, you have an interconnect with endpoints that would represent the gates of the transistor gates on the receiving logic gates. And our interest is to find an estimate for the time in propagation to the endpoints or to some intermediate points that we may have here. So a few things. Remember, we're dealing only with a tree, so there is a unique path between the voltage source and any of these endpoints. And the second, we split all the couplings, meaning in reality, and that is more than ever true today, you have significant couplings between wires. And in that sense, obviously, you may have to split a number of them. Let's not discuss how to do it. In the old days, the simplest way to do it, you took a capacitance between two nodes, you divided by half, assign 1/2 to each one of the nodes, and you ground it. But let's assume we have the tree here. So let's look at the very simplest case, because that will give you an idea of what could be happening here. Oops, I clicked twice. My apologies. So let's look at the very simple case that would be one voltage source, one resistance, and one capacitance. I'm sure all of you are going to remember this as the very first circuit that you analyze in your first class in circuit theory. And you can see there are many ways, of course, of solving this. We're putting a constant step function, okay? VDD is the height. The solution is the voltage time once minus this exponential of minus t over RC. And we'll see the many ways to get this. So if we begin to advance t until, you know, this capacitor that's initially is at 0 and the voltage that it gets charged, if we took at 0.7 RC, you have moved half of the voltage upwards. And if you go to t equals to RC, you get 63% of the VDD there. There are many ways to solve this. You can check the equation. The equation comes from literally you take the sum of the voltages on this loop has to be 0. The current here is equal to C dV to dt. So you get RC times the derivative of the voltage plus the voltage equal to the source voltage. You can take the Laplace transform, then the transfer function is 1 divided by 1 plus SRC. The Laplace of a step function is 1 over S times the voltage here, and so on. And one way to solve it would be to take the inverse transform of the transfer function times the input function. Whatever way you do it, you get that exponential. And let's do a little bit of analysis here. The first part that we can do is these are all linear circuits, so let's not keep writing VDD. Let's put it equal to 1. All voltages will be between 0 and 1. If the 50% point now indicates when the voltage is equal to 1/2, as the initial voltage is 0, this would be the integral of the derivative between 0 and that point. So the observation of Elmore in the late 40s was this median point, can we approximate it instead by the mean and the mean of the variation of the voltage? So the definition of Elmore delay is this mean t times dv to dt computed between 0 and infinity. Let's analyze why it makes sense to do this analogy with the probability density, and we'll see how that holds as we go forward. One way to do it is you take the derivative of t times the voltage, you get t times dv to dt plus dt to dt, that is 1 times the voltage, the product, the derivative of a product, and we keep going. And if we do a graph, we can see the following. We start at 0. There is a steady monotonic rise, and as t approaches infinity, the voltage approaches 1. This tells you that, exponential tells you that. But now come the more interesting observations. The derivative is positive, and it decreases in this case. It starts pretty steep, and it goes to 0 as the curve flattens. This is an exception because it's the case that we are connected to a voltage source. The general case, you're going to see a 0 rising and becoming 0 again. So the voltage can be interpreted as the cumulative density, and the variation of the voltage, dv to dt, as the probability density, and the analogy is perfect. Then you can say, let's compute the mean of this probability density. And in this simple case, as we have the explicit formula, we get RC. So far, so good. Very trivial computations, nothing very interesting here. But now we can do something more tricky. We can try to define and compute this mean, meaning the Elmore delay, without explicitly calculating the formula for V of t. And this is very important because if we try to apply this to a tree, we cannot have a closed formula for the differential equation. It's extremely difficult. You can get it eventually, but as you can see, it's a very convoluted computation. So let's try to do a trick. Let's define W as the voltage minus 1. The derivative doesn't change. We take this integral of this partial, this product. Then as t at 0 will give us 0 for this product, we get tau times, V of tau minus 1 equal to this integral that is giving us the Elmore delay plus or minus, as I inverted, said 1 minus V. Now comes the second observation that will be needed, is that if we send the time to infinity, this product goes to 0 because V approaches 1 very quickly, much faster than any power because it's an exponential, negative exponential. So you can see that if this goes to 0, we can send tau to infinity, and then we get that the Elmore delay that is here is equal to this 1 minus V of t at the end. And the 1 minus V of t is where we do have a differential equation for it. It is RC times the derivative. We have the initial conditions for the derivative, and we get that the Elmore delay is RC because V of 0 is 0, V of infinity is 1, so we get exactly this. But the interesting part is we were able to compute this mean, this t times dv to dt, without explicitly writing the equation for V. We only needed the exponential behavior of the approach to 1 and all of that so that we could get that product to go to 0. An observation, if you take the Laplace transform and try to do some expansions, the Laplace of a derivative is this, V of 0 is 0, so we get this. So if we try to compute h of s, the transfer function, we have two observations here that is a little bit of an aside. If we expand H, is an analytic function around s equals 0. If we expand it this way, we get the first momentum that is called. And a warning, in some papers, this moment MKs get sometimes divided by 1 over k factorial to make it more analogous to an exponential. I kept them straight. And if you, on the other hand, take the formula for this Laplace transform and you expand the exponential into the series of the exponential, you get, again, here the first term as the Elmore delay. And if you compare these two, you see that TD, except for sign, is equal to this first momentum. And that's why the Elmore delay in many papers is referred as the response of to the transfer function first moment and so on. As the literature uses this, I wanted to mention this is how you get it. So now let's get back to the tree and let's get to work. How can we generalize the formula? Number one. Number two, do we have the analogy to a probability distribution and a cumulative density? So taking the mean makes sense. Third, does the voltage at the endpoints approaches 1 fast enough so that we could repeat this trick of the integral going to 0 that allows us to do this computation? So let's try to see what we can do. Notice again that going from here to an endpoint, there is a unique path. And if we apply the Kirchhoff voltage law to this loop, we should get a 0. So let's try to see how we can compute these numbers, that this is what we're interested in. So the loop is very simple. We get the path to the end, the current times the resistance, the voltage at the end, and this has to be equal to the voltage at the source. So I wrote the equation this way. I'm using Kirchhoff's voltage law. The currents in the capacitors are equal to, C times the derivative. And now we're dealing with vector equations because we have all the voltages. One is the vector only with ones, and I'm using the transpose as I'm writing them horizontally, because if not, I would need a slide per equation. So if we do these substitutions, we end up with something of the type, the voltage at the end, this VLs, this V in, I replaced it by the constant one, and this gives us something with the C's, the capacitors, that only multiply their own voltage. So this matrix C is a diagonal, and we have a matrix of resistances that is not a diagonal, and we'll look at that. But we get a very similar equation, conceptually speaking, a first order differential equation for the vector of the voltages. All that we did, as I said, we replace here this voltage, these current sources are now, to get the currents this way. And I'm going to take a look now. How do we compute this matrix R? And I'll give you the formula and then we'll proceed to the derivation. As we have a unique path between the node 0, that is the voltage, and any node K, we can take the intersection. If we take nodes K and H, we can take the intersection of those two paths. If the paths are as divergent as possible, the intersection will be only the first resistance. If there is more common elements, there will be a larger intersection. We take this intersection, we call it the path PKH, and we take the sum of all those resistances, and the formula for the Elmore delay will be that multiplying the capacitor at the end of it, and the sum is over all capacitors. we are going to do the whole elaboration on why at the end we end up with this, but I'm giving you the formula at the beginning. And let's take a very simple example to see how that comes. Instead of the very simple example of 1RC, I take the first part that we could have a trivial branch, two of them going. If you apply what I said, the voltage sum to 0 on this loop, we get this. We replace this current by this derivative here. Now the point is that we have to replace this one. And this splits into 3. Here they are. And then if we do the multiplication and substitute, the observation comes here. For the endpoint, we get the whole path, R1 plus R2. But for these branches, the R3 doesn't count because we multiply by only R1 here. So this gives us the intersection between this path and this path is the R1. The intersection with itself is the R1 plus R2. The intersection to here is only R1, and this gives us the I'm trying, I don't know if you see them very well, colors for the dots. These 3 nodes are the same. The red dot and the orange dot are 2 different nodes. So this tells you more or less a very simple case. So now let's look at the general case. And I reorder the tree. This is the one that I'm interested in looking. So I put it at a straight line. And at every one of these intermediate nodes, they could be a branch. But the only interesting observation here is that on any of these branches, the current coming up here has to be equal to the sum of the currents on the capacitors hanging in here, because those are the only current sources that we have going on this branch. So the current coming here has to be the sum of the current of all capacitors on this branch. So using that, we can see that that current has to be, I'm calling branch L here. This would be the sum of all the capacitors in the branch. And you notice that the branch will be hanging with these R's that would be exactly the R's in the intersection of the path from here to here to the path to any of these ones in here. So with that, we are allowed to get this, the formula that I was telling you. And here you can see it a little bit more explicitly how the current coming out here gets split between this one here, the one in the branch here, and the one continuing along the path. We do the substitutions, and this gives us essentially the elements of the matrix, the coordinate. Reminder, the initial condition, we are looking at the case of starting with everything discharged. So based on this, let's try to look at this matrix R and try to see what can we get. Of course, we're looking after an exponential behavior, and an exponential behavior in a case of a matrix, we would have to look for eigenvalues of the matrix and see if we could solve the equation in a certain way. The analysis, oops, what happened here? I did something that enlarged the.
You have to.
I do a minus.
A minus. Not the minus on the top. No.
Okay, I got it here. I think this is okay. Oops, that's the wrong one. Restored. Okay, I think we're okay here.
No, now you touch the screen sharing.
And I'm supposed not to touch it.
No, because the slides are on the system.
Oh, so what do I hit now?
You hit on the right, you touch the screen sharing button to...
Stop sharing. Okay.
Okay, now it's okay.
Back to, hey, thank you. My apologies. So let's go back to the matrix R, and we find the first thing that is interesting, of course, is a real matrix. The coefficients are real, and it's symmetric by construction. The intersection of the path between node H and node K is the same as between node K and node H. So it's a symmetric matrix, a positive element, and so the basic theorem in linear algebra that you may remember, even though I'll get back to it later, a symmetric matrix has n real eigenvalues. So we have real eigenvalues, counting multiplicities, n, and n eigenvectors that will be perpendicular, actually. So very nice. The matrix R could not be better. It has some diagonal dominance characteristics by construction. You can see that very easily. The full path adds all the resistances, the others add partially, so it's less. But we have one negative thing. We have the matrix C. Even though it is a diagonal matrix, these capacitors are different in value. So R and C do not commute. So we cannot find a set of common eigenvectors. So we have to be very careful trying to get this exponential behavior correctly to make sense, because, as I said, R will have a set of eigenvalues, but RC we don't know. So let's keep going and see where do we get so far. So far, we have the equation, first order. We have a nice R matrix C. We have an initial condition, the vector 1 for the initial voltage. The current source gives you 1 there. Now let's look at, if we take this limit as t goes to 0 from the right, you get that the initial voltages will be RC times the derivative at 0. We'll use that later, nothing very tricky. But unfortunately, as I said, because of that non-commutative property, it's not easy to derive much more. So we're going to look at the inverse of R, but we're going to derive it directly because it's much easier than inverting the matrix. So if we use, instead of voltage equals resistance time a current, we can look at the conductance, meaning the reciprocal of the resistance, and say the current is equal to the conductance time the voltage. The nice part of that is that we can now will take Kirchhoff's current law, and the matrix is much more localized because you need only differences of the voltages, and those go one node ahead at a time, as you will see. So the current at every node, the sum of the currents has to be 0. And we start looking at that. We look at, for example, at the first node, we have the different currents, the current from the capacitor, the current due from the difference of the voltages times the conductance. Now we look one up. That's where it says up from the node, the difference in voltages. And if we expand this G1, we add it here, we get all the conductances at the node times this voltage, and we get all the ones up, and we get this extra term G1. In general, this will tell you that that capacitance current will be equal to the sum of the conductances at the node, that's local, as you see, the sum all the ones up, and the one behind. So if we write this in matrix form, it's very similar, but I'm writing it instead of RC dV to dt, I'm putting C equal dV to dt GV plus these terms coming from the initial condition that I wrote A times U, initial condition V0. The term AU will make it explicit. It's very simple. As you can imagine, it's a constant because of that. But this equation allows us to do some nice things. Again, the matrix G, now let's try to look at the derivation of it, and it's simply we note that there is a conductance only if the nodes are connected, and if not, you don't get a contribution there. And it's exactly symmetric because the resistance between H and K when they are contiguous is the same as K and H, and it's this conductance, no problem. We get positive entries outside of the diagonal. The metric is symmetric. Again, can be diagonalized, very nice, but again, G and C do not commute, so we have the same. But now we have some more interesting things. The diagonal terms, as we saw, we get a negative sign, and it's the sum of all the G's incident to that node. So if the next node or any node is not a leaf node, we have that the absolute value here is bigger than this because it includes all of the resistances at that node, but the other is only the ones connected one ahead. So we see that the absolute value of the diagonal is negative, is bigger than the ones of the rest of the row. Except in the case that we're at a leaf node, because this is a tree, so we have only one resistance there, so the two are equal, the absolute value is equal to that connecting node. So symmetric matrix, it has n real eigenvalues, can be diagonalized, it has some dominance characteristics, no commutation here again. So where did we get with all of this? The first part is that we're going to bite the bullet, and even though these are not the eigenvalues that we need, we're going to prove that they are negative. And the way to do it is really very simple. You never teach theorems like this in a class in linear algebra unless you get to a more sophisticated ones. But if you think of an eigenvalue, it's something that multiplies the vector. So you can try to see that the eigenvalue cannot be much larger than the sum of the coordinates of the matrix in a very, rough way. So if you have an eigenvector x, gx equal lambda x, that is not 0, it must have a largest coordinate that we can assume it to be positive, because if not, we can change x by minus x. So let's assume this is the most positive one. All the others, this quotient for the other coordinates is smaller than 1. We write the equation for that coordinate. We take the division, and we see very clearly this is actually the proof of Gershwin theorem. It's a theorem from the 1930s that became popular later with control theory. We see that we get the diagonal term and the terms of the diagonal multiplied by something that is smaller than 1. So clearly, if we have a non-leaf node, this term is more negative than the sum of this, and these are even multiplied by factors smaller than 1. So clearly, the number is negative because this quantity dominates and is negative. In the case that is a leaf node, if you remember, we said that it was equal. So in that case, theoretically it's true, could be equal, but then you apply the theorem to the one before the end point, and again you get the lambda equals 0. So interestingly, all eigenvalues of G are negative counting multiplicities. We rediscover G should be invertible. The determinant is the product of the eigenvalues. C is a diagonal matrix. All the capacitors are positive and grounded. So we made some progress, and we'll repeat the analysis that we're on the right track. The exponentials are smelling like negative. The term AU, if you go to the computation, is very simple. It's V times this, and the V is equal to 1. So the term AU, it gets multiplied by the first conductance. So we have two equations, the one that we obtained from Kirchhoff voltage law here, and the one that we obtained from Kirchhoff's current law, if you want, same initial condition. And from here, as G is invertible, you can see you get RU equal to 1, R equals G minus 1, and we computed the inverse of the resistance matrix, but in a different way by doing it explicitly here. So far, so good, but we have not made the, we have to zoom in now, but we got some nice things in this analysis. First than anything, we have a, I think that you, let's see, how can I get it? Multi-user, undo annotation, oh, minus, here we are, good. So we are, remember, we have a nice differential equation with constant coefficients, initial condition. If you remember your first class on differential equations, when you have an equation of this type, the solution is you have to find a special solution, and then you take the homogeneous equation, meaning you put AU equal to 0, and you're done. And very easily you see by having compute the AU term that a constant solution is okay. It doesn't satisfy the differential, the initial condition, but it satisfies the differential equation. So if you put V equal the constant, that this is, if you think, the final value that the nodes are going to have when P approaches infinity, that's a special solution. So good. So we're left with the homogeneous equation. We eliminate the term AU. This is the equation with initial condition equal to 0. Now here comes the first observation that these capacitors are scaling the voltage in a funny way. If all the capacitors were equal, C would be a perfect diagonal, the same constant. It would be commuting, and we would have no problem. The eigenvalue with the G will simply get scaled by 1 over C, and we will be in business. This observation is in the original papers. What comes, for some reason, it escaped. That is the following. Let's try to get good information from the equation, and the information that we get is interesting because we have an equation that is very nice for T bigger than 0, is infinitely differentiable and everything. We're considering limits only for the right. So if we try to take the equation and as V of 0 is 0, and we take the limit from the right, we get that the voltages initially are 0, except the one in the voltage source, the next one, meaning that's where it gets propagated instantaneously. That's why sometimes people say that this is the putting a delta, a Dirac delta of that value there, but I'm not going to use that. The only one that is different is, as I say, the voltage connected to the source, and the others are 0. By continuity, you get that this voltage dV1, at least as it is bigger than 0, is 0 a little bit. The others we don't know. Of course, we expect that the derivatives are going to be growing because the voltage is rising, but let's try to prove that. If we take the second derivative and we keep going, and we get that in coordinates, and that tells you that the second derivative, taking the limit from the rights, are positive. So that also will tell you then that for those nodes, except the very first one, the second derivative is positive. That tells you that the voltage is monotonically increasing at the beginning. Very nice so far. This is what the probability distribution should be having. But in truth, we have something much more interesting. And this in the classical papers is done in a different way that appeals to a much more complicated theorem. If you remember, the exponential of a real number is always positive. So we can take the exponential of a matrix and we could try to see is it positive or not, meaning are the coordinates of the exponential of a matrix positive? And the answer is no, except under a special condition that we're going to see. So if we try to simplify here and I put B for C minus 1G, this is the initial condition. You notice that the components of the initial condition are all positive. And here is where a little bit of more elaborate linear algebra tells. The GIKH were positive, divided by C's that are positive are also positive, except the diagonal. If we take the exponential of a matrix, if you remember this is convergent and so on, the solution should be E of TB times the initial condition. And these exponentials have all the entries positive if the terms of the diagonal of B are positive. You can see the proof in Bellman or other books, but the proof is very simple. Exponential of matrices behave very much like exponentials of numbers, meaning A of A plus B is E to the A times E to the B, if the matrices E and B commute. And in that case, everything works. You multiply by a very large number negative so that the diagonal becomes positive, and E to the TB is equal to this. As I say, everything commutes. And then you get that E to the TB is the product of true matrices with only non-negative entries. So we get a positive matrix. The converse, by the way, the converse is also true. You have the proof there by doing a continuity argument. We don't need that. So that tells you that the solution to this differential equation for the derivative, the initial condition is positive. The matrix has only positive entries. So this cannot be but positive. So this implies something very interesting. All the dV to dTs are positive going forward, so the voltage will be monotonically increasing and so on. So far, we achieved then that these voltages behave very much like a probability density. The part that is missing is, does this approach one fast enough? And our suspicion is yes, but we have to do it. So let me remind you a little bit about eigenvalues and a little variation here. The most interesting proof in engineering, in my opinion, of that the symmetric matrix has real eigenvalues is when you use the Rayleigh quotient, and you can see it in any book. But the argument is very simple. if you take a vector W in 2 dimensions and you apply a matrix to it, you get that the inner product of these two would be, the absolute value times the cosine of the angle. So this would be the formula. The maximum value that you're going to get here is when the cosine is equal to 1 of -1, meaning the angle is 0 or pi. They are collinear. If they are collinear, it is an eigenvector. So that's really how you prove this. It's more, the mathematics is more sophisticated, but also you see that the perpendicular plane, will appear here. And the proof of that is very simple. You take, you are going to get a set of orthogonal eigenvectors. The numbers will be real. They will be perpendicular. And the way that you do this is that you take, instead of just the circle, you have to go to the n-dimensional sphere. You define this function. The n-dimensional sphere, meaning the vectors of norm 1, is a compact set. So meaning bounded and closed. F is continuous, obviously. So it has a maximum. And that maximum has norm 1 here. You produce a curve over that sphere by taking a perpendicular vector and doing cosine plus sine. You can take the derivative. This is just the product, so you get the derivative of the curve times the curve plus the derivative of the curve time. And you can, as the matrix is symmetric, you can pass it to the other side and you get this. This is the only point that you use the fact that A is symmetric. This has to be 0. So A of U is perpendicular to all vectors perpendicular to U. That means that it has to be collinear with U. It's a eigenvector real, and then you apply the same argument to the perpendicular space that is dimension n-1, and iteratively you get the fact. So why did I go through that trouble? For the following reason, that if we go back to the original equation, we have C minus 1 is this, we could take, as opposed to the sum of the squares of the matrix, we could scale them by the capacitance. This behaves exactly the way as the normal inner product, except that now we would be working in an oval. In the case of the two-dimensional plane, it would be an ellipse. And exactly the same derivative argument applies, and you get the minimum and everything, except in this case, instead of being perpendicular, you get that G of U, you get a set of eigenvectors, eigenvalues that are real now for C minus 1G, so I wrote them this way. But instead of the U's being perpendicular, they are perpendicular in this new metric. But there are n eigenvectors. They form a basis. They are quote perpendicular in this new metric in the oval. And now we have the solution, because now we can take these eigenvalues. In this case, as I change the sign, they're positive so that we can clearly see the negative exponential. You use Gershwin exactly the same way, except for the scaling of the C. And now we are in good shape because we have this set of vectors with negative exponentials as you go. By doing that, we have the general solution. We have to adjust the constants to be 0. the lambdas go to 0 at infinity. The lambdas are positive, so E minus. We adjust for the initial condition. We have to solve for the alphas. And now we see that the voltage approaches 1 monotonically with this exponential decay rate. So this limit T1 minus V goes to 0. This is all that we needed to repeat the argument, evaluating the integrals. So let's see what we did. We saw that the components V go monotonically from 0 to 1, but derivatives are positive, so we can think of the voltages as the cumulative density of the probability. I didn't do this, that's a more sophisticated argument. We can prove that actually these probability distributions are unimodal, meaning they rise, they get to a maximum, and they decrease. And this is the point that they start at 0 and they end at 0. They are positive and unimodal. This argument is not made very clearly in the papers. You appeal to some general theorems. So I've never seen the explicit derivation that there is a set of eigenvectors, eigenvalues that are really negative. You don't need the powers of T, and this is unimodal. We repeat exactly the same argument. We take the original equation. V at 0 is 1, V at infinity is V at 0 is 0, sorry. V at infinity is 1. We saw the explicit expression for the matrix RC, that is this. So we calculated the Elmore delay completely, and we completed the analogy to a probability distribution. So to conclude, what did we do here? We didn't use very much from electrical engineering, except of course the most basic statements: what is a resistor, what is a capacitor, Kirchhoff voltage and current law. We heavily use, of course, the case of a tree that was used several places, explicitly the symmetry of the matrices. We established the behavior of dV to dt as a probability density and V as a cumulative density, and the very fast approach to 1 at infinity, and that allows us to do the limit and compute it. The rest was relatively simple math. You know, we use some linear algebra and differential equations. All the linear algebra is finite dimensional and fairly easy to establish. We did not need to solve for V of t, and we did not have to appeal to more sophisticated network properties like passivity, reciprocity, and impulse responses and all that. Of course, this limits the scope of the analysis, but it clarifies the dependency. The current ways to do delay estimates that are based on the so-called Krylov-Arnoldi projections into subspaces, you could try to do projections on the subspaces of these vectors that are the ones that are perpendicular, weighted by the capacitance matrix. I have not seen that done explicitly. I'm not sure what is the result. I did have the bibliography from you. The classic paper, of course, is the Penfield Rubinstein. There are extensions of that time to other cases and all that, and this gives you a little bit of the flavor of that. So thank you very much. That concludes my talk. I didn't leave much time for questions, but Rafael, I think you take over. If there are questions or any comments, I'll be happy to answer. As I said, if anybody wants the more complete set of slides, send me an email. I'll be happy to send them to you.
Thank you, Professor Antun. I'm going back with my camera now. So we have time for questions. You can always put your questions on YouTube. I have a question regarding if you have second order circuits, for example, if you have RLC parasitics, can you do something within this new framework that sort of re-explain what Elmore delay is really all about? Do you think that some of the path you took here hold?
Well, the part that you would have to be very careful is the following, that given that every time you introduce an L, you have a second order equation, then you get the part of the, oops, I did think something wrong, but anyways, can you see me?
We can no longer see you now. I guess you have to turn on your camera again.
Did I turn it on again? Let me see. Okay, let's see if that works better. But anyways, remember when you have a second order differential equation, you're going to get sine and cosines and the exponential. So you're going to have oscillations of the derivative. So the analogy to a probability density will not hold completely. The fact that if you manage to make sure that the exponentials are negative, you probably have a fast convergence at infinity, so you could try to do some approximations. But the perfect analogy that I think was the insight of Elmore, that you have a probability distribution here in a sense, and it's unimodal actually in these cases, it would not hold.
Okay. Your conductance matrices that you showed us before, they are quite similar to the matrices that are employed on modified nodal analysis, for example, that is used.
Yes.
So could you use, or is this being used already? I'm not sure. The pre-processing steps of an electrical simulator to help you computing the Elmore delay, for instance?
Well, yeah. It gets used a lot for trying to do RC reductions, as you say. Actually, there is a very nice example of this in the book of Alberto Sangiovanni and Jacob White on the G's for a case. And the part that I have not seen, that this is what puzzled me, is the following, that in the case of trees in particular, you see, you do have this complete set of eigenvectors for the C-1G. And I have never seen them used explicitly. Now, these are very large matrices, so be calculating those eigenvectors is not a very practical thing, but I have never seen anybody that took explicit advantage of this case. But yes, you are correct. These are the matrices that get used in FastPy simulators very heavily to do the initial reductions.
Yeah, and as a, let's say, corollary of this question is that the naive approach, let's say, to Elmore delay is to, assemble the tree from your netlist and then compute by doing a depth walk or something like that. From your new framework, let's say, what do you think what would be takeaways to implementing a better or faster Elmore delay computing engine?
Oh, well, remember that the calculations that you have to do to compute some of those RCs is exactly the same. There is nothing new here. The part that could be interesting is the following, that if you studied the behavior of those eigenvectors, by looking better at the eigenvalues, to prove unimodality, for example, you do have to take a look at which eigenvalue is larger and all that to make sure that this dv to dt have only one peak point. So, for example, you could try to do a faster approximation by saying that after certain points you don't need some terms and try to reduce matrices. The reason that this is still interesting is that in logic synthesis, particularly as you are resynthesizing with coarse placements, you do use Elmore repetitively to try to, estimate delays, simplify the logic, re-estimate delays. And there is where maybe if you had a better approximation to the first 2 or 3 eigenvalues, that could give you a much faster computation. But I haven't done that, by the way. I did all this after I left Synopsys, so I didn't have a team that I could try this, try that. But I'm sure there are possibilities of that there.
It is my impression that after you left the company, you started to look into the fundamentals of what you were doing in the past, right?
Well, you have more time to read papers with a fine comb. And as I said, the papers are correct. I mean, I talked to Mark Horowitz about this, and it's simply a way of how much physics do you want to use versus how much mathematics. And as given my path was much more mathematical than physics, I wanted to clean up the math, but it doesn't mean that it's better or the results are the same at the end. If not, we have a problem on one of the two sides.
Yeah.
But you can find different things depending on your approach.
Okay. Elias, who is a student of Ricardo, asks the following. Thanks for the presentation. Beautiful applications of linear algebra and ODEs. Is there any study using chaos theory?
To try to see what happens with some variations and all that. I have never seen one. To tell you the truth, it's kind of odd because a number of these things, if you look at the slide, if you can still see the slide that I have, those papers of John Wyatt, at that time in the mid-80s, that there were still ECL circuits, people tried to do extensions to meshes and things like that, and then the field sort of got abandoned. The theorem that I quoted for the CG, the different perpendicularity weight, is in the book of Peter Lax on linear algebra. That book is an incredibly interesting book for more out-of-the-way applications. The reason that it doesn't get used is that Peter Lax was a brilliant mathematician that did a lot in partial differential equations at NYU. That book is notes that some students took of a class that he gave, and the book never got cleaned up, proofread, completed. So it's a very interesting book, but it's hard to use as a textbook because suddenly arguments are missing and things. But you can look there. There are many interesting applications. The other book is Bellman, but Bellman, was a brilliant mathematician that what was trivial for him was not trivial for most people. So it's hard to read in that sense.
Okay, so thank you once again for being here virtually with us. We hope that you can come to Porto Alegre anytime after all of that goes away. We hope it does.
If I can apply this to develop a vaccine for the coronavirus, you'll have me there soon, but I doubt it.
I guess
okay.
That's what everyone is thinking now, how to, cooperating in any way possible. But so our contribution here is to bring people together in this time. So thank you.
Thanks to you. A pleasure to talk to everybody.